Okay, so welcome everybody for this Hassel lecture with very nice weather today, and thank you for being here, preferring to hear about chemistry. And okay, this is the 48th Hassel lecture on today's 24th of May, 2018. And distinguished Professor Matthias Beller from Germany. And ladies and gentlemen, I wish you all warm welcome to this section. On behalf of the Department of Chemistry and Norwegian Chemical Society, I have the pleasure of wishing you all welcome to the Hassel lecture for 2018, which is number 48 in the series. The lecture will be given by Professor Matthias Beller, sitting just behind, from the Leibniz-Institut for Catalysis, LICAT in Rostock, Germany, where he is actually currently also the director. Before introducing Professor Beller, I would like to give a short biography of the Nobel laureate Professor Odd Hassel of this chemistry department. The lecture series was initiated in 1967 on the occasion of Hassel's 70th birthday. Professor Hassel, who was born on May 17th, 1897 and studied in Oslo, where he received his Candidat Real degree in chemistry in 1920. Later, he went to Berlin, to the Kaiser Wilhelm Institute in Dahlem, to conduct X-ray crystallographic studies. He obtained a doctoral degree from the Berlin University in 1924. He returned to Oslo to work as an Universität stipendiat at the University of Oslo from July 25. 1 year later, he became a docent of physical chemistry, and in 1934, he became professor of physical chemistry at the University of Oslo, where he stayed for the rest of his career. Hassel published a large number of papers in structural chemistry. During his very first years in Oslo, he dealt with problems from inorganic chemistry. From 1930 and onwards, his work concentrated on problems connected to molecular structure, in particular his pioneering work on the conformation of cyclohexane and derivatives. His first groundbreaking paper in this area was published in 1943, and the final crystallographic refinement was ready in 1947. In later years, he also made similar contributions to the structure of charge transfer complexes. Professor Hassel was awarded the Nobel Prize in Chemistry in 1969 for his work on the structures and conformations of organic molecules. He shared the prize with Sir Derek Barton, professor of organic chemistry at Imperial College at that time in London. Hassel passed away in May 11, 1981. It is in his memory that this lecture series is continued. The selected Hassel lectures were initially structural chemists working in areas more or less close to Professor Hassel's activities. But in more recent years, a broader range of chemists have been invited. This is in accord with chemistry's constant developments to tackle rising challenges in our modern society towards a more efficient and cleaner chemical processes, as will most certainly will be apparent from today's Hassel lecture. And now, a few words about our eminent guests, the Hassel lecturer of today. Matthias Beller studied chemistry at the University of Göttingen in Germany, where he completed his PhD thesis in 1989 under the supervision of Professor L.F. Tietz. After spending a year with Barry Sharpless at MIT, USA, Beller worked in the industry from 1991 to 1995. As I got to know, that was at Höchst. Then he moved to the Technical University of Munich as professor for inorganic chemistry. In 1998, he relocated to Rostock to head the Institute of Organic Catalysis, which became in 2006 the Leibniz-Institut for Catalysis. The work of his group has been published in over 800 original publications, reviews, and over 100 patent applications. He won several awards, including the Leibniz Prize for the DFG, the Paul Ruelander Award of the Organic Reaction Catalysis Society of the USA, and the Carl Ziegler Prize for the German Chemical Society. In 2006, He was awarded the German Federal Cross of Merit. Besides, he received the first European prize for sustainable chemistry and was appointed to honorary doctor of the University of Antwerp and University of Rennes. In 2017, Professor Beller has received the Carl Ziegler Prize from the GDC, German Chemical Society, and I think I have cited this already. I just jumped the line, sorry. And I think, Professor Beller, without wasting more of your precious time, I believe that our audience and myself are looking very much forward to your lecture for the 48th Hassel lecture, which bears the title, Technologies for the Sustainable World Beyond 2030, What are the Contributions from Chemistry and Catalysis? The floor is yours. Welcome.
Yes. Yeah. Dear Mamo, thank you very much for these very kind words. Of course, I would like to start thanking you, Mats, the other colleagues from the selection committee. It's really a great honor being here. 2 weeks ago, you sent me a mail, said, I'll promise we will succeed in good weather for you. And I should say you really succeeded in that promise. I will talk a little bit about climate also at a later point. It doesn't have only negative impact, of course, as we can see today. So, but coming back to the Hassel lecture, it's a great honor for me. I really appreciate that selection. And I remember very well, I've been a few years ago here at the University of Oslo at a research meeting, and I remember the campus and the area, and I appreciate also Oslo. It's a wonderful city, of course, and it's a great occasion for me to come back actually to this very nice place. So today I would like to tell you a little bit about the possibilities of chemistry and especially catalysis for solving problems or to contribute to solving problems for our future. Tomorrow, I will, of course, show some chemistry also in that, but I will be more general. Tomorrow, I will go more into details, some of our work, especially which relates the work or the similarities, but also the differences between homogeneous and heterogeneous catalysis. So if you're interested in that, so I can also invite you to the lecture tomorrow also. But now, coming to the point. Okay. I'm not sure what is your feeling when you look at the daily newspaper. So my feeling very often is this one. So we see lots and lots of negative news. In fact, we got the feeling never has been a time on Earth where it was so dangerous, so difficult, like nowadays. This is, of course, not true. And I'd like to show you also in my lecture that because of the advancements in science and engineering over the past century especially, but also in the prediction of the future, we are able to solve most of the problems which we consider very important today or which we have considered to be important in the past. Just one example at this point. The statistical average age on Earth, if you were born 100 years ago, your statistical life expectancy at that time was 33 to 35 years, depending on the source you're looking at. 2 years ago, if you were born on Earth, again, on a global scale, the statistical life expectancy, not only for Norwegians, but for everyone on Earth, was more than 65 years. And so within 1 century, we doubled the life expectancy of mankind. And that's, of course, is a great achievement. And this was only possible actually because of the advancement of technologies and especially also of basic science understanding. Because basic science, today I will talk at the very end of my talk about application also, so bringing things from basic to application. We should never forget, if we want to bring things from basic science to applications, we need understanding. And therefore also, of course, education and basic research are very important. So let's have a look at our Earth, let's say, from a more pessimistic view first. So one of the biggest problems we face in the next years is that at the moment we are performing our economy, we are performing our lives out of equilibrium. In fact, what do I mean when I say we are performing our lives out of equilibrium? I mean we are using more resources than are rebuilt. This is a scale, and you see more or less it's of course an overall statistics. It shows you, let's say, how many in a broad sense, how many resources on Earth are used at a certain time. And until the 1980s, we are more or less in equilibrium. You could say we use so much resources like at the same time we're rebuilt. But since the 1980s, we are running out of equilibrium. And we are currently somewhat here. And we are using resources in a sense as if we have 1.6 or 1.7 Earths available. But we don't have 1.6 or 1.7 Earths available. We only have one Earth available. And it's absolutely clear, if you do calculation, this cannot go on forever. At a certain time, now one can debate how close this time is. So probably for me it will be still okay. For the younger ones, might be not. So it's clear this cannot continue go on forever. So I think the most challenging or the most important problem is actually creating jobs, having, let's say, enough food on Earth, having, let's say, good life conditions, and all these things, but under the condition of, let's say, equilibrium. And that's a dramatic challenge. And again, you will see how science and technologies can contribute actually to these questions. So why? I apologize for some German. This is a slide, or this is a scheme from a very recent presentation of the German Academy of Sciences on artificial photosynthesis. So it was presented just a week ago. In 2 or 3 weeks, there will be an English version also on the web. That's a statement of the German Academy of Sciences on the possibilities of artificial photosynthesis. So the English slide was not available at that time, so I apologize for the German here, but I think it will be understandable for you also in this context. So why are we using more resources than are rebuilt? Because most, let's say, of our materials which we use for energy creation, but also for other things, they are fossil-based fuels. And what you see basically here, there's coal, gas, hydropower. This is with respect to energy. Relatively little on a global scale is renewable energy. And of course, there is oil. If you look how energy, the consumption of energy developed over the years, then it's also clear that we cannot continue like in the past. Because if what we all expect, what we all hope for, if there is no major catastrophe in the next year, most likely until 2050, the use of energy, the consumption of energy, even if we think about saving energy and if we use LEDs instead of normal light, etc., it still will continue, the consumption of energy will still grow, and probably around 2015, we will use double the amount of energy which we use today. And then now, if you think about if we're using the same technologies today, if we're using the same technologies which we use today in 2015, it's absolutely clear it's not working anymore. That's because we simply, not that we have enough resources. We have lots of coal and oil and gas, and you know this very well here in Norway. So it probably this will continue for the next few hundred years. But the real problem will be carbon dioxide. Because if we produce double the amount of energy fossil-based compared to today, the increase of carbon dioxide in the atmosphere will rise dramatically, and this will lead to consequences which we cannot actually predict at the moment. So often people think, when talking about material use or fossil use, it's the problem that these resources will not last forever. It's true, they will not last forever. But as you know probably also very well, predictions from the past have been often false. So if you look 50 years ago, then prediction at that time already said we will not have enough oil or coal already today. But as you can see, the price is still reasonable. We have enough, and also we will have enough for the next 50 years. And probably again, exploration will make clear that we will have still enough cheap fossil-based resources in 100 or 200 years, not to talk about coal, which lasts even much longer. But the real problem, in my opinion, from the fossil-based fuels is the carbon dioxide. And we have a rise of carbon dioxide since pre-industrial times. So we have 290 ppm in the atmosphere in pre-industrial times, and since a few years, for the first time, we have steadily, all over the year, amounts of more than 400 ppm of carbon dioxide in our atmosphere. 98 out of 100 climate researchers say we have climate change because of the rise of carbon dioxide. 98, not 100 out of 100. So I'm not a climate researcher here, but I think it's very reasonable to believe there is climate change ongoing, and it's mainly a result of the increase of carbon dioxide. And again, climate change, I should be also very clear here, it's like everything in life, it's not something only negative. Like every coin has two sides, things in life has also two sides. And climate change has advantages and disadvantages. But we should really take care about the disadvantages. And one of the disadvantages of climate change is that it will change, for example, agricultural yields all over the world. It will change the weather and it will change agricultural yields. And it's also clear in the area of climate change, there is winners and there is losers. And if you look, let's say, because of the climate change, there is an increase in agricultural production, plant increase, simply because the temperature rises on the northern hemisphere, or in most countries on the northern hemisphere. So also, Norway will benefit from that. And I think we don't mind if we have more weather like this. But what is the risk of climate changes, of course, is that a lot of the countries which are already poor, especially in Africa, they will see dramatic loss, actually, of agriculture, which will increase poverty there and increase the problems. So you see already we have these problems moving people from Africa to Europe, and this might increase because of climate change in the next years, again, dramatically. And nobody really wants that. On the other hand, it's not clear how the rise of carbon dioxide will lead to more weather extremes. Subjectively, I think everyone feels there is more weather extremes, more tornadoes, more things. You read about this in the press everywhere. But in my opinion, it's not really clear. It's likely, but I'm not sure if it's 100% clear. So, and if we want to avoid these problems, then of course we have to reduce the concentration of carbon dioxide, or we have to change technologies. This is a vision for sustainable chemical industry, but I should be also very clear, I had it on the slide, but I didn't mention that, I should be also very clear here, only 3% at the moment of the fossil-based fuels, or of the materials the fossil-based materials which we use, are used for chemistry. So we cannot, this one should make also very clear, we cannot use or produce enough chemicals from carbon dioxide to solve the carbon dioxide problem from energy generation. It's impossible because the amount of chemistry what chemistry uses, it's simply too small. Nevertheless, I think a sustainable chemical industry is also an important point. And this is the view how a sustainable chemical industry could look like. With the increasing availability of renewable energy, and I will come to that point also in a few minutes, with the increasing availability of renewable energy and the availability, of course, of salt water and seawater, we have the possibilities to produce oxygen and hydrogen. Instead of hydrogen, we can also say reductants, because what we often do not realize, or at least in a general sense we don't realize, we take the oxygen for free. Oxygen is in our atmosphere, so oxidations, it's common. The problem is to make reductants. And if you find a cheap way to make reductants, this is very interesting for energy generation, for, let's say, carbon neutral energy cycles, and so on. And the cheapest way to make reductants is probably by water electrolysis or photo electrolysis of water to produce hydrogen. With the availability of carbon dioxide, initially from industry, you can think about steel production, concrete factories, of course, produce lots of carbon dioxide. Existing power plants, of course, you have, let's say, a concentrated carbon dioxide exhaust gases available. You can use this carbon dioxide as a carbon source with the reductants to produce basically all the goods which make our life more healthy, more safe, more easy, and so on. And this is not, let's say, a dream vision. Most of the technologies which are in these steps here, they already exist. The key point is it should be commercially viable and competitive to existing processes using this, and in these processes preparing these. I will give you some examples later on. I assume most of you are chemists, but nevertheless, for those who are not chemists or not related to chemistry, a brief introduction to catalysis, because you have seen on this slide, if we think about these conversions, everywhere is written catalysis. Why is there catalysis? Catalysis in principle is nothing positive, but a catalyst, you want to do a transformation here, you add a catalyst. It costs money, you have to take it away again. So why you are doing that? You're doing that because catalysis allows for the control of chemical reactivity. This is the great thing. So imagine you would like to convert your starting materials, which have a certain energy content, to some products. We're thinking here about an exothermic reaction, so we create energy, which is free, so normally it should happen. But it doesn't happen. It doesn't happen because, fortunately it doesn't happen because otherwise I would not stand here, you would not sit here, we would be all carbon dioxide. So there is a nice kinetic barrier going carbon-hydrogen bonds to thermodynamically more stable carbon-oxygen bonds. And this normally doesn't take, so the reaction simply doesn't take place. We are existing, so we are stable. But if you add, let's say, a certain compound, a certain principle, the reaction pathway changes. The energy is lowered, so you don't have to climb over the hill. You're going somewhat underneath. And it's possible now you have enough energy, or the molecules have enough energy so that they convert to the product. And that, despite all the negative things about catalysis, it's expensive and purification and so on. If you look at modern processes in the chemical and pharmaceutical or life science industries, 9 out of 10 processes, if you look at processes from the last 20 years or so, they make use of this principle. So catalysis, in that sense, also is a key technology for sustainability, for achieving sustainability, because you can work under milder conditions, you need less energy, you produce less waste and so, but on the other hand, it's used dramatically in industry. So what type of transformations now are of interest for a sustainable future? And on the next slide, I show you a purely subjective personal view on some simple transformation. If I would give today, tomorrow I will talk a little bit also about, let's say, bioactive compound drug molecules or so, which is also an interesting area. And I could give you also a list, let's say, of the 10 most interesting reactions for drug discovery or so. But today I'm focusing more, let's say, on this simple reaction on bulk chemical processes. And synthetic chemists among you might say, where's the challenge? No stereoselectivity in here, no chiral chemistry involved. But if you look at the specific reactions, although they look structurally simple, they are very important or can be very important. I already pointed out water splitting. It's an important process because it allows you to produce, of course, in an endothermic reaction, hydrogen from water. Today, 3 to 4% of the hydrogen is produced by water electrolysis. We will see if it increases in the future. I will come back to that point in another minute. Valorization of carbon dioxide, and I would like to talk a little bit from chemistry perspective now in the next slide about valorization of carbon dioxide especially. Carbon dioxide to carbon monoxide, you might say, oh, we're using carbon dioxide to make an even more toxic molecule because carbon monoxide, it's in our exhaust gases. We all know about the toxicity. But carbon monoxide is a fantastic C1 building block for industry. And there's lots of, let's say, large bulk chemical processes which make use of carbon monoxide. Not only talk about carbonylation, which is double-digit number of million tons of carbonylation project. There is Fischer-Tropsch. You can imagine if one can do it efficiently, one can think about carbon dioxide to carbon monoxide via Fischer-Tropsch to, let's say, green fuels, green kerosene, and so on. So there's lots of opportunities. And the great thing is, industry uses carbon monoxide. So if you can do this efficiently, you have already the following up technologies, all available, and you don't need to do any, let's say, further steps there. This might be a strange reaction to you, or looking at this. We have carbon dioxide, and then we have coal here, which again produces carbon dioxide. Why did I mention that reaction? I mentioned this as an example for, let's say, more efficient reforming processes. And I will also come back in my lecture in a few slides, let's say, to the point of reforming processes, which is an important point for valorization of carbon dioxide. And then you can think about selective reactions, making olefins, alcohols from carbon dioxide. You can think about carbon dioxide to methanol. Methanol in the last decade, we discussed this just before lunch. In the last decade, there has been several multi-100,000-ton plants in China installed, converting methanol to propylene, because then you have already propylene and if you use carbon dioxide as a resource for that, then you basically have a carbon dioxide or a carbon neutral based propylene, and propylene, you can make ethylene and butenes from that, so you have C2, C3, C4, so you have the major building blocks of the chemical industry relatively easy from carbon dioxide available. Low energy reforming, I will come to that point. Artificial photosynthesis, personally, I believe it's a very important topic. And I will also elaborate on the advantages and disadvantages of photosynthesis. It sounds a bit crazy. If you think about, there is billions of years, nature developed our photosynthesis system. And now we are coming and saying, okay, let's make an artificial better one. Can we do that? You will see later on, I believe we can do that. And in principle, artificial photosynthesis for me means converting renewable energy to compounds with carbon-carbon bonds. And also that, I believe, it's a very important point. There's elementary steps, there's basic science needed for such reactions, but there is also industrial perspective in that. So let's get a bit more in detail with carbon dioxide. Often people who don't know carbon dioxide, they say, or you hear, it's difficult to activate. Of course, carbon dioxide is the thermodynamic sink of carbon compounds, but it's not difficult to activate. Anyone who does a Grignard reaction knows, and we had the discussion this morning, anyone who knows who does a Grignard reaction knows that carbon dioxide reacts at room temperature, 1 bar, nothing special, with an organometallic magnesium compound, or an organomagnesium compound, the Grignard reaction. The problem of carbon dioxide is it's not the activation, because with any type of strong nucleophile, you can attack this electrophilic carbon. And by the way, I find the concept very interesting of the umpolung of the carbon dioxide, which is studied here. But what is not easily possible is doing this, let's say, in an economically viable, industrially viable manner. So if you look at the industrialized processes for carbon dioxide, here you see some reactions. This is beautiful organic synthetic chemistry. And what typically is done there, it makes use of energy-rich, let's say, compounds to drive this thermodynamic sink somewhat uphill and to allow for reactivity. But these reactions, it will be very difficult, if at all, to make them, let's say, on a larger scale or to commercialize them, because if you need a stoichiometric amount of a zinc reagent or a bore reagent or even a manganese reagent, and you make stoichiometric amount of manganese salts, if you want to make 100,000 tons, what to do with the 100,000 tons of manganese salts? That's not so easy. So what I want to say with this slide is there is beautiful synthetic chemistry with carbon dioxide developed over the years. But what is really needed, it's conversion, upgrading of carbon dioxide in an economically viable manner. And how can we do that? We can do that, at the moment, we are doing that if we stay on the same oxidation scheme. So making carbonates from carbon dioxide. There's nice new plastics also. That's, of course, then we don't need strong energy, additional energy. Or there is things, if we use cheap reductants, let's say like hydrogen or electrons. Then again, also bulk applications come into mind. One example from our own work, this is unpublished work, so very recent work, still writing the paper, it just should show you what you could do in this area, for example, is photocatalytic reduction of carbon dioxide. And here I've shown you, so the influence of different, let's say, catalysts on this reaction. So the commercial titanium dioxide, P25, which you can buy from Evonik, but also other industrial companies, it doesn't show any reactivity, let's say, for carbon dioxide reduction. Of course, we know since the seminal work at the beginning of the 70s about, let's say, water splitting, using titanium dioxide in the presence of UV light, etc. But you can also do the reduction with carbon dioxide, but you need specific types of titanium dioxide. And we recently discovered that, for example, aerogels, which have a much larger surface area, allows for this type of transformation. And then if you impregnate copper, then basically you can generate carbon monoxide to a significant extent. You also do some water splitting, because this is carbon dioxide, it's an aqueous solution, which we use there, or you can think about carbon dioxide in a water droplet in the atmosphere, and we're reducing that. You might understand, when you think about chemical reactivity, that if we want to reduce carbon dioxide or want to reduce water, it's more easy to reduce the water, because protons are more easy to reduce. And this is what you see here in the result. We produce relatively significant amount of hydrogen from the water, but a little bit also the carbon dioxide. But then we found a very interesting discovery. And this is shown basically here. And I cut here a long story short. If you have questions, you can talk to me afterwards, or we can have a discussion in the afternoon or tomorrow. We found that the addition of oxygen improves the selectivity and the productivity for carbon dioxide reduction. For those who are chemists now, they might think this is very strange. Because if you think how easy it is to reduce oxygen compared to carbon dioxide. So now we are adding something which is much, much more easy to reduce. So we're adding an oxidant, in fact, but we improve the reduction pathway for that. How can you explain that? We can explain that actually by the distribution of the active species. We believe it needs, apart from kappa 0 species on the surface, it needs also kappa 1 species, and the oxygen, in fact, oxidizes part of the catalyst to the kappa 1, and that system then becomes more productive. But that's a very interesting fun. So more or less we have basically aerobic conditions here. So we're doing carbon dioxide reduction under atmosphere. So this is something, I think, a very interesting basic finding also, which I have not seen in the literature. I have not found any precedent to that. That's something, for example, what we're doing. Another thing, what we are looking into is reforming process. Because in the end, as I said, if you want to use carbon dioxide in industry on a larger scale also, you have to think about cheap ways to do reforming. And I will show you two examples here. This is one. This is a process for making formates. Formates are used as fertilizers also. They are produced on 600 to 800,000 tons at the moment. And they are mainly produced at the moment from carbon monoxide, adding methanol to that, and then hydrolysis of the compound. This is the process BASF is, for example, doing, but also other companies. So we developed a process where we use, instead of carbon monoxide, we use carbonates. So carbonates is, of course, it's the oxidation state of carbon dioxide. We use carbonates in the presence of methanol and a base. And then you generate, let's say, in 100% carbon efficient way, formate from that. So 2 molecules of carbonate or carbon dioxide are reduced to the oxidation of CO or formate, and 1 molecule are reduced, and 1 molecule of methanol is oxidized at the same time to make another molecule of formate. So this is what I call reforming. So you have carbon in an oxidized form, carbon dioxide here, and carbon in a reduced form, methanol, both relatively cheap compounds. You combine them and you produce the oxidation state in between. And this you do under relatively mild conditions, 130 to 150 degrees, which is for reforming relatively mild conditions. And based on this chemistry, then you can use carbon dioxide to make not only formates, but you can also do carbonylation reactions. This is a reaction, I will talk more about that tomorrow again. This is a reaction which is used. There is 2 plants, industrial plants, again, multi-100,000 ton scale. In Jurong Island in Singapore is one, and another one is in Saudi Arabia. A 3rd plant is currently built for the production of methyl methacrylate. Methyl methacrylate, you know, probably is the monomer for plastics, methacrylates. And there is several ways to make methyl methacrylate. One of the industrial ways is carbonylation of ethylene to make methylpropionate, and then condensation with a basic halide. With formaldehyde, you get methyl methacrylate. We discovered that instead of carbon monoxide, you can use carbon dioxide in this reaction. And if you look now at this equation, then you should get the feeling something strange there. And of course, it's not stoichiometrically correct, because methanol in our reaction, again, is the reductant, or is also the reductant for the carbonylation process. You can, before I show you this, you can make lots of carboxylic acid derivatives, but the important point is shown here. Again, the key point is also to understand this process, to improve it, to bring it to an, let's say, viable or economically viable manner. So if you use labeled carbon dioxide and an olefin and methanol, then you observe 92% yield of the corresponding ester. And you observe that 82% of this ester carries the labeled carbon from the carbon dioxide. So this carbon dioxide molecule ends up here as an ester. But at the same time, we have nearly 20% of non-labeled. Where does it come from? It comes from methanol, because the catalyst dehydrogenates methanol to formaldehyde, The hydrogen reduces carbon dioxide in this process. The formaldehyde is dehydrogenated again to produce CO, non-labeled CO, and the non-labeled CO then goes into the product here. So in principle, it means you can use carbon dioxide and methanol, if you have an equilibrating catalyst available, as a source for carbon monoxide. And now you might say, why is this important? Carbon monoxide, if you have it on site in an industrial plant, it's no problem. It's cheap, it's easily available. But transporting carbon monoxide is very difficult. If you look at the internet, you will find an interesting story. You just have to give in the names Bayer CO pipeline. Because they wanted to build a CO pipeline for the German Ruhrgebiet, some parts, some kilometers. There were lots of public protests against that. No CO pipeline through our gardens, and in the end it was impossible. I think it's technically feasible, but the public doesn't tolerate this. So if you really want to use CO at a remote place where you don't have, let's say, carbon monoxide on large scale available, the combination of carbon dioxide and methanol, it offers you an easy possibility to generate carbon monoxide or to use it in carbonylation processes. In the interest of time, I'll probably skip this. Just a few remarks to methanol, because carbon dioxide to methanol, this is already done today. You might know about the Ola demonstration plant in Iceland, who's doing that. But in reality, all the industrial plants for methanol, they use 1% to 2% of carbon dioxide in their feed, because it improves the conversion. And because of that, people are interested in using pure carbon dioxide for making methanol. And if you have methanol, again, this is for itself, it's 200 million ton scale product. But in addition to that, you know the concept of a methanol economy. In principle, you can trace this methanol economy back also to carbon dioxide and allow actually the production of chemicals, but also fuels from carbon dioxide. Just a short remark also to the differences between homogeneous and heterogeneous catalysts. This will be the main topic of tomorrow. The differences between homogeneous and heterogeneous catalysis are manifold. I don't want to go into detail about that today, but typically heterogeneous catalysts, they are more stable, but they work under much more drastic conditions. So this is the heterogeneous catalyst. Still the mechanism of this reaction, although it's done on 200 million ton scale, it's not totally clear. There's still debate about the mechanism. There is, if you use a homogeneous catalyst system for this reaction, normally they work under milder conditions, but they are not as productive typically. And only in recent years, significant progress has been made in this area. But this might also improve again. Let's say, the commercial process. And we have, at the moment, we are working on a project also together with a catalyst producer to come up with a totally new concept for carbon dioxide, hydrogenation to methanol, with a homogeneous system on a commercially viable way. We developed the first non-noble metal catalyst, but as Mats yesterday evening said very correctly, it's not only the metal which counts, it's the ligand. You always have to look at the price of your overall catalytic system. And also in this case, the triphos ligand, which is very special here, it's an expensive ligand for this type of chemistry. Nevertheless, and I again will elaborate more tomorrow on that, why you can do same type of reaction with a ruthenium and with a cobalt catalyst with the same type of ligands. So how important is really the metal and how important is the ligand? But in principle, you can do that. Let me tell you a little bit about energy. Because so far I talked about chemistry, but I also said before, in principle, chemistry only makes 3% out of the fossil-based resources which we are using. So I talked about this tiny 3%. Nevertheless, these 3% are also pretty large on its own, and the chemical industry is important on its own. But the real driver, or the real important area, is of course energy. And I'm convinced that in the future, energy technologies will be much more related to chemistry than in the past. Of course, if we use gasoline or coal and we burn it, it's a chemical process. Nevertheless, energy generation was never really very much attached to chemistry. Of course, the exhaust gases and things like that might be, but it was not really. In the future, this will change because there's lots of, I think, a key issue for converting light, electrons into chemical energy carriers. It requires chemical knowledge and it requires also chemistry technologies. So let's talk about energy. This is a different slide to my third slide. It shows you again, 12 billion tons oil equivalent goes to energy and only 3% of that goes to chemistry. So now we're talking about this large share. And there is a very nice saying of Albert Einstein, it's foolish to repeat the same experiment and to hope for different results. So if we want to reduce the amount of carbon dioxide, it doesn't make sense to continue with fossil-based fuels. By the way, sometimes when you're in your first organic practical course, it might be different from this statement. Okay. Back to the topic. It's a very nice statement. We have to look for different technologies. And this is, of course, what's available. If I would be from Norway, I would probably show hydropower because you have fantastic possibilities here with hydropower. And I found it always interesting from a concept. So Norway is exporting so much gas and oil, but at the same time, it's fully renewable with the hydropower. So in the future, of course, if we want to go to carbon neutral energy generation, we have to go to renewable energy. And in northern Germany, it's mainly wind. In other places of the world, it may be mainly wind. And in other areas, it may be mainly photovoltaics. There might be some geothermy. Hydropower at the moment, I believe, is already pretty much used. So it will be difficult to increase it significantly. Of course, it will be increased to some, but we can probably not double, triple, or even improve it by an order of magnitude and so on. But here we definitely have the possibilities. And this is a picture from the German government, so I again apologize from the German in the slide because it's from the federal government. This is the prediction. It was, you see, it's more or less 10 years ago. And if you this was the prediction 10 years ago to what we will use in the future. So this is wind energy for Germany, the most, I would say, significant one, because we are not the most sunniest country in the world, something which you probably also experience. But we have lots of wind on the coastline. Bioenergy is increasing. At the moment, I would say cost competitive-wise, it falls back compared to the other areas. But also photovoltaics is increasing. And interestingly, if you look at the price development of these renewable energies, there was a dramatic reduction over the past decade, probably past 20 years. And now we are very close to prices per kilowatt hour for renewable energy, which are close, let's say, to prices from fossil-based fuels, like in Germany, for example, Russian gas also, or Australian coal. So interestingly, 15 years ago, I would say nobody would have really predicted this dramatic decrease. And so renewable energy becomes really available. In fact, we are ahead of plan at the moment, which, by the way, is a problem for the German consumer because he has to pay the tax. The price is relatively low, but the tax is high for that. That creates a problem also of acceptance of these technologies for some people in the public. So this looks very good. The real problem with that, of course, is another one. The real problem of that is the flexibility, the dynamics. For catalysis, dynamics is important. For the energy system, dynamics is terrible. Imagine, or I can show you, if you look at the web, again, you can see, for example, you can see how much kilowatt hours on a certain day in Germany come from renewable and how much come from fossil-based. And if you look at the morning at a certain day and in the evening, it might change dramatically, because in the morning probably you have lots of wind on the coastline, all the windmills are going, and in the evening, no wind. So what to do? Okay, we use the energy only when it's available? Of course not. So we have to find ways to convert this renewable energy in stable energy carriers. Of course, we can now say supercapacitors or so electrons, but electrons are terribly to store. They are not very efficient, as you will see. So the solution is to go to chemical storage, chemical compounds. And in that sense, again, chemistry comes into the game. By the way, already, if you look at the installed wind power in northern Germany at the moment, if you have no wind in the morning and lots of wind in the evening, it means that you put in 7 to 8 fully operating power plants onto the grid. So within 12 hours, you have to have this flexibility. So they need some buffering. And of course, I know also there's the concept sending electricity to Norway, pumping it up, sending it back the other. So there's lots of possibilities, of course. But at the moment, nobody really knows what will be the final solution. And probably there will be more than one solution. And because this is a very important issue, I always compare it a little bit like a horse race. So in a horse race, you have certain favorites, which might win the game. But then you have outsiders also. You never know. And if you have now a very important race, on whom would you bet? And the energy problem is a very important race, so we better bet on each of and look into each possibility, and then decide what is the best technology or the most economically viable. In the end, by the way, it might be more than one winner. So if I talk about energy storage, I come to photosynthesis. I mentioned that before. Photosynthesis is a fantastic process. Scientifically very interesting, still lots of things to discover. But efficiency-wise, it's a terrible process. This often people don't realize, who don't know that. If I ask you and you don't know, how much of the energy of a photon, you have, let's say, a certain photon, and how much of its energy in the end ends up as storable organic matter? So,
6 to 8%.
So theoretical efficiency is 5 to 6.6, says from what I know from it. But this is the average. Of course, there's high energy crops and things like that. But the reality is less than 1%, statistical average. So less than 1% of your energy, which you have in your photon, ends up as chemical storage. And now I'm coming to the point of artificial photosynthesis. So nature didn't optimize the system with respect to efficiency. Even here in Oslo today, if you look at the chlorophyll unit of the plants over there, the photosynthesis center will be only stable for half an hour to an hour or so. Then it's rebuilt. It needs energy to be rebuilt. Already today, as chemists, we can do better. Go to the internet, buy a commercially, or go to Home Depot, buy a commercially available photovoltaic device. You can buy it. Good one, 18%. Go to consumer electronics, or again to the internet, buy water electrolyzer. You can also buy that, also not too expensive. Combine the two, you can do that. You have an efficiency of photon to chemical energy, in that case hydrogen, of nearly 10%. By a factor of 20 better. Of course, hydrogen is not organic matter, but it's much more efficient than photosynthesis. And if you think along these lines now, not only to produce hydrogen, but other energy carriers, then you might understand why it's important that artificial photosynthesis can be interesting. So the easiest chemical energy carrier, or the first chemical energy carrier from wherever you start, renewable energy from electrons, is most of the time hydrogen. We could think about carbon monoxide also, but it's more toxic. But most of the time, people consider hydrogen as the first one. Hydrogen is the most available molecule in the universe. But We cannot, like yesterday evening said, dig it out of our Earth. It's a gas. It even will diffuse in space. So it's the smallest molecule which we know, and it has very specific properties. So in order to use hydrogen, we need special technologies. We can use compressed hydrogen. We can use liquid hydrogen when we need lots of energy for cooling. We can think about cryoadsorption, new materials, lots of possibilities also for chemistry and materials. And we can think about chemical storage. We can think about metal hydrides used by the US Army and several other armies probably. We can think about ammonia, things like that. And we can think about organic hydrides or organic compounds. And as an organic, synthetic, organic chemist by training, I especially like this area because these are the things we are using also today. So these are the technologies which we are using. So what we are doing, I have a group in my group, which is totally, let's say, devoted using on hydrogen technology, let me say it. Henrik Junge is the group leader in that group, and what we are doing is hydrogen generation, apart from photocatalytic CO2 reduction. We do reactions of carbon dioxide with hydrogen to make chemical energy storage. We're focusing on methanol, formic acid, a little bit methane also, and then we release the energy again if we want to use it for certain purposes. So transportation, for example. And in this concept, you produce your hydrogen from renewable energy, you store it ideally in a liquid or solid compound easily, and when you want to remove it again or want to use it, you use it in a fuel cell, which is the most efficient way to convert chemical energy again to electricity. Of course, one should be very clear. Each of these steps costs energy and costs money. And this will be the big challenge to implement the thing. So we have to improve each of these steps to make it commercially available in the end to the buying or using of fossil-based fuels. This is the key point. A few comments to the different energy carriers. And I start, let's say, with some of you might consider an esoteric compound, because this is not one of, let's say, the most prominent energy carriers, but I believe it's an interesting one. Formic acid. Formic acid has the advantage, it's the first reduction step from carbon dioxide, and it has the oxidation state, let me call it, of carbon monoxide. It's the only reduction product of carbon dioxide where you not intrinsically lose energy to make water. Because if you go from carbon dioxide to methanol, you need 2 hydrogen atoms to make 1 molecule of water. And this energy, which makes the reaction thermodynamically more favorable, you lose in the process. And if you go to methane, you need even 4 hydrogen atoms to make 2 molecules of water in that system. So for the reduction of carbon dioxide to methane, it's not CO2 plus 2H2 to CH4, it's 4H2. So you need lots of hydrogen for that. That's of course and in this sense, of course, carbon dioxide has an advantage. Carbon dioxide, on the other hand, it's the only compound which I know which more or less thermoneutrally can add hydrogen and also release hydrogen, organic compound. Because depending on the condition, this process in both directions is more or less thermoneutral. And this is for an energy carrier, again, a fantastic thing. If the process is thermoneutral, you intrinsically lose not that energy in the process. You make it. The nice thing is formic acid, it's not toxic. If you look at it's corrosive. So you should not put your hand in the system. So you can ask also what is better toxicity. Methanol, for example, is toxic but not corrosive. What do you like more? But if you handle it appropriately, it's okay. So we developed together with Gabor Laurenci for the first time the concept of a so-called hydrogen battery, where we inside the battery produced actually formates as hydrogen storage material. What we did, I want to explain it here. So you have a catalyst, let's say, and you have an aqueous solution. And now you put in 600 bar of hydrogen, so a lot. Okay, this is compressed hydrogen. What happens now is, under the conditions, there's the catalyst and water, the carbon dioxide, the hydrogen reacts with carbon dioxide or with carbonates to build formates, so your pressure goes down. So you have the same energy content like in the compressed hydrogen, but at much lower pressure. Of course, it doesn't go to 1 bar because it's in equilibrium depending on the condition, but it goes down. And now you release the hydrogen by using it in a fuel cell, for example. Then the formate goes back to hydrogen. So in principle, in this way, you have a catalytic battery where you use or where you transform your hydrogen into formates in situ. Of course, this was the first demonstration, and in order to make such thing commercially available, you have millions of turnovers which you need to run in a motor, for example, and you would not use a homogeneous but a heterogeneous. But in principle, it's possible. You can also use non-noble metals for doing the hydrogenation of carbon dioxide and the dehydrogenation process. And we demonstrated for the first time that simple iron-based compounds, again, the ligand is more expensive here than the iron, definitely. But it's in principle, this was the first, let's say, non-noble metal or iron-based complex which, with respect to efficiency, could compete with noble metal systems. And you can also, with a non-noble metal system, you can fairly, let's say, efficiently doing this type of hydrogenation, redox dehydrogenation processes. We looked very carefully into the process. It's what you typically do if you're doing homogeneous catalysis. In addition to that, more recently, we developed heterogeneous systems for this type of reaction. This is, again, will be a topic of tomorrow. We pyrolyzed molecular organic frameworks on stable inorganic supports, and these materials, they also do very efficiently hydrogenation, dehydrogenation process. So you can do it both with molecular defined and non-molecular defined systems. Okay, so we're getting closer to the end. You're getting hungry, probably. I'm not sure who had already lunch. I hadn't, so far. So, okay, what is your preferred food? Let's make, so, a real vote. Who is for broccoli? Ah, influenced by modern culture, I would say. I should clearly say I like this more. But I will explain you why in a minute. I'll give you an explanation why. So let's think a little bit about the energy content of material. This is the volumetric energy, that means energy per liter. This is energy per kilogram. And you see, 1 kilogram of hydrogen is fantastic, but hydrogen is a gas. So 1 liter of hydrogen is lousy. That's the problem of hydrogen. The good things are here. If you don't talk about fusion and things like that, this is the chemical picture here. Fusion would be here somewhere also, but it's 50 years ahead still. 50 years ago, it was 50 years ahead. Today, again, it's 50 years ahead. So this is the organic things. You see, that's also the reason why we are using them. They are good gravimetric and volumetric energy carriers. This is lithium-ion batteries. Of course, it has advantages, but the energy content, that is clear. It's the advantage, the big advantage in these systems is the oxygen. We don't need the oxidant in the system because it's in the air, so we can simply burn it. In a battery, you need that also. So here is formic acid. So also to be clear, formic acid, I'm not saying it will replace this, but it might be a competition to lithium-ion battery type things. This is Killingsboller. So this area here. And this is, and therefore I like for me, broccoli. So broccoli has pretty much the same energy content like formic acid. And Skillingsboller is something here in the range of alcohols and things like that, what we all like. So, and I believe our body also still knows that, because 50 years ago we did not know in an hour we will have lunch or so, or this evening we will have dinner. Very nice, but we did not know this 10,000 years ago. And evolution-wise, we are not much different from that time. So we like the things which have energy. That's my expression for Just a few remaining slides. So because of the energy content, of course, we're not only looking for formic acid, and we're also looking at more energy-rich content, compounds where we try to build the cycles. Methanol or alcohols is one. We don't make artificial sweets, so far not. But so, for example, we looked for carbon dioxide to methanol and methanol to carbon dioxide, for example. We developed, this is also an interesting case. Before our work, the state-of-the-art catalyst was developed by Dumessage. It was a platinum nanoparticles, but we should show that we could develop a system, which you see here basically, this type of structure, and if it's related to the complex you have on the first slide, and you will hear more about these type of complexes tomorrow. It's this complex, it's this specific type of complexes which allows for low temperature reforming processes of methanol, for example. If you have questions, I'm happy to answer that. But the key point in this chemistry, like in lots of catalysis, it's the following, and this is my final message here, for scientific one. Catalysis is not a phenomenon like we typically, in my opinion, like we typically teach this in our students. There's the metal, and then everything takes place in this metal, like in hydroformylation or hydrogenation, the famous Wilkinson complex. I think this is rather the exception. Catalysis is a multidisciplinary phenomenon. It's lots of things working together on a surface. There is cooperative catalysis all over, with real catalysts in industry, but also with homogeneous systems, as you will see tomorrow. And this, I think, this is also the future of catalysis, because one end or one metal center will not be able to move the stick. But if they work together, so again, this is more general, if we work together, we can achieve much more. So this is what I wanted to tell you from a general perspective. Very briefly, our institute, I'm attached to the university. I teach at the university, but our institute is independent. And what we are trying to do is to build this bridge between fundamental basic research and application. So we typically have around 40 cooperation per year with industry. And I will show you very briefly 3 examples which made the transfer into industry. If you have questions to that, you can ask me afterwards. The first one, on the next slide, this is a little bit about the history. It started 1955. Now we have half homogeneous, half heterogeneous catalysis people. It's around 300 people working in the institute. And 3 examples which are related also to some of the work I talked today. This is a cooperation with a spin-off company, Exitron, and they won the Green Tech Award in Germany, startup company. They are selling this type of reactors for energy storage. So they have nice engineering, let's say, benefit in their system. And what they do basically is they convert renewable energy to methane, but also methanol. And they sell this for energy storage in single family homes, for example. And there is several hundred homes which have been, which are using this principle at the moment. This is a typical problem which we are facing, because very often industrial partners come to us and they ask a specific question. And this is a chemical, for example, now you make 1,2-pentadiol. The organic chemists know what this is, but this is a typical, let's say, question. It's an important platform chemical for flavor and fragrances, where the cooperation with Symrise, which is among the top 3 companies worldwide for flavor and fragrances. And if the synthetic chemists, they might think about how to do that. Okay, most would say probably 1-pentene, epoxide, dihydroxylation, or epoxide, hydrolysis, or dihydroxylation, and so on. This is the way we think in academics. In industry, you think a little bit different again. So to make it more green, you start from a renewable C5 building block. Furfuryl alcohol is available from fructose, so at reasonable price. And then you do a hydrogenation and deoxygenation reaction. And this is a one-step process. And you see, this is the project development. The first trials have been done 2011. 2014, the plant design started. And this year, a 10,000 ton scale plant using this technology will be finished in Kentucky in the US, because the company acquired there another company which produces fructose. So this catalyst will be used from probably the second half of this year on a 10,000 ton scale. And my last example is a process for making methyl methacrylate. I already mentioned that. It's carbonylation processes. We developed a new catalyst for that. Tomorrow I will tell the details about that. We were able to improve this chemistry for other interesting industrial feedstocks, and that's also an important point for sustainability. At the moment, this mixture of products is called dibutene. It's produced on multi-million ton scale. And this mixture is hydroformylated to alcohols. And 10 to 15% of this mixture do not react because these are highly hindered olefins. And so you have 100 to 150,000 tons of unreacted olefins where nobody knows what to do with it. So what happens? They simply use it thermally. They burn it. And we found a catalyst which is able to transform this. So it saves basically 150,000 tons, or it allows for the use of 150,000 ton scale of substrate for valorization. And that's, of course, also with respect to sustainability an important point. In catalysis, it's often like in life. So today I showed you some examples. And I don't want to finish here without saying it needs basic science, it needs understanding, but it also needs lots of work. And I only presented you successful cases, and probably also tomorrow most of the time. It looks so easy at the very beginning, but one should never forget it also lots of work behind that. And of course, it needs dedicated people, which you will see on that. So I said at the very beginning, we have lots of problems. I hope I could show you that there is, if we advance science and technologies, there is possibilities to solve this problem. And we can talk about other problems too. I always compare it, let's say, with a glass of water, half glass of water. So most people might say half empty, or some say half full, but there is other people's also about this. But in the time, let's say, where science also has to compete with fake news and other things, we should be always clear also to the public that you need, let's say, data, scientific data, because scientists try, let's say, try to answer questions, and we don't, let's say, use emotions in these results. And in that sense, I believe our future is much brighter than we typically expect. Because if you look, I said this at the very beginning, doubled life expectancy. But it's not only life expectancy. If you look at most of the important parameters, hunger, you might not know, 300 years ago, 20% of the population in France, 20% of the population in Finland, I don't know about Norway at that time, died because of hunger at the end of the 17th century. There was crisis because the harvesting was for several years not very good, and 20% of the population of the countries died because of hunger. I assume nobody of us here really expected real hunger. If we look at diseases, of course, not everything can be cured, but we have made dramatic progresses with, and hunger, diseases, these were key problems for mankind. And for the first time in history, we have, let's say, for the majority of the population on the planet, we have solved us. We have significantly improved the situation. And so, also money-wise, the situation is much better than compared to previous centuries. So in principle, we have a much better situation. But it's often not outspoken. We only talk about the negative things. But we should make clear, in order also to get funding and also to do science and research, we make clear to the public that in the past decades and centuries, this contributed to to the development. And I think this is also a point scientists have to say very clearly. And chemistry is especially important because chemistry is the #1 science who makes most innovation for other industries. It's not electronics, engineering, electrotechnics, engineering, etc. It's chemistry. Chemistry allows for innovation in all kinds of areas, drug development, materials, if you think about your cell phones, information technology, computers, and in the future also probably significantly energy technology. And that offers lots of possibilities for chemistry. So this I wanted to say. This is a final statement from the founder of our research organization, Gottfried Wilhelm Leibniz. He said one day after awakening, I had so many ideas that the whole day was not enough to write them down. So especially the students, I wish this for the future. And I'd like to thank you for this invitation. I talked too long, but this is my second last slide now. This is a final riddle. And for those of you who don't know the solution yet, who see this riddle for the first time, so the ones who know, please don't answer. Think about it. So, because I think this is a nice way also how we solve scientific things. We are trained in a certain way, and if we look at this, what is the number? So we're 16, 6, 68, 16, 6, okay, 10 minus, but 62 plus, 88, 98. So we double, divide. What is the mathematical relationship then? This is what we're doing normally. But what we have to do, sometimes we have to step back from and try to look from the thing from a different angle. And then it becomes very easy. 86, 88, 89, 90. And now everybody knows what is the number below the car. And that's also what we have to do in science, I believe. Because sometimes we are trained in a certain way, especially we look in a certain way, but sometimes we have to take a little bit of free time, step back, and try to look from a different angle or to bring in ideas from a different angle. And then everything becomes much more easy. Thank you very much. I'm happy to answer questions.
Thank you very much, Matthias, for a very nice lecture. And I think we will have a few questions. And the microphone somewhere. Any question? If there are any.
So I apologize that I talked too long. But there is no silly questions, I should also say. So if you didn't understand anything, you can also come to me afterwards, of course.
Yes.
Yes.
By there.
I understand you.
I just have a general question about the use of carbon dioxide in catalysis in general, especially for energy storage.
Yes.
Do we consider the effect of on the demand for fossil fuels when we create systems that can turn the waste from fossil fuels into a commodity?
Yes. So in principle, if you want to use the waste from fossil fuels is, of course, you can say carbon dioxide. And if you want to convert this into commodities, I think already today a number of processes is close to commercial viability. The problem at the moment is, first of all, you compete, let's say, with an existing plant, so you have to do additional investment. If you think about using carbon, let me make this as an example, formate, 800,000 ton scale. So reasonable, not let's say methanol, but reasonable scale. If you look at the cost, because we did this very precisely or very carefully, if you look at the cost for the conversion of carbon dioxide to formates, the price determining factor is hydrogen in that process. If you look at the cost of the current methanol process, the cost determining factor is carbon monoxide. Carbon monoxide and carbon dioxide, because 96 to 97% at the moment of synthesis gas is produced by reforming processes, coal gasification, alkane reforming process, etc. They are related. So there is not so much difference, in fact. The moment there would be a global carbon dioxide tax, I think most of the formate would be produced from carbon dioxide. At the moment, there is not, let's say, a real benefit. It's a new technology. I had this morning also a discussion with somebody from industry, and often this is also misunderstood in the public. People think industry likes to do new processes or may come up with new products. I was 6 years in industry, and I can tell you the thing industry likes the least is making a new product with a new technology. What they really like is, let's say, you have your product, you make a process improvement, double the outcome of your plant with that, and don't change anything. This is what industry really likes. Industry is very conservative, at least the large bulk industrial or large bulk international industry. If we talk about small spin-offs or startups, it's different. But let's say established international companies, they are not very risky with respect to technologies. They say, okay, let's do a startup. If they're really successful, we buy them. That's the strategy. So you need some, let's say, pressure on that also. And that can be legislation. But unfortunately, only makes sense if we do this on a global scale. If we have a carbon dioxide tax in Norway or in Germany or in Europe, things will move to Asia or in the US and will be made even in a less, let's say, environmentally benign way. But in principle, it's possible, it's close. But at the moment, so there is no clear view on the carbon dioxide price in the future, because people think if you now would like to get 500,000 tons of carbon dioxide, it's not so easy to get them. And what is the price of that? That is also the reason why people using, for the methanol process, only 1 to 2% of the carbon dioxide, because synthesis gas is, again, more easily available. But in principle, I think there is possibilities.
Thank you very much for, I think Matthias has answered that very well. Matthias will be still available today and tomorrow for the extra Hassel lecture. And if you have any discussions or wishing to ask questions or get special details, just get in touch, please. And to thank you once again, Matthias, so I have to present you on behalf of the Hassel Lecture Committee with Kristallchemie von Odd Hassel, which is actually the 48th exemplar of the dissertation of Professor Hassel, which is only printed in 100 items, and this is luckily in German.
Oh.
And thank you very much for, for accepting our invitation.
No,
and please join me again to thank Professor Hassel for this nice lecture.
Thank you very much. Thank you.